We're going to continue on with another method for solving a quadratic. If we think about some of the stuff we've done already, you could graph a quadratic. You have to know where the solutions are, kind of what you're looking for. It's a little time consuming. Not all the answers are great. If you're using technology, it's a decent method. You could type something into Desmos, and really what we're looking for is those x-intercepts. Or in some other situations, you might be looking at where, like a system, where the quadratic is crossing something else. The second method that we have goes back to junior high. If you're trying to undo just a normal square, if you just had like x squared equals 100, you could do the square root. So in the nice cases, like extremely nice case where there's just an x squared, you can just use a square root. The third method is that factoring that we talked about. So if you could break it up, and this is again assuming it is factorable, which not everything is. And I'll talk more about going backwards and how you would know if something was factorable with what we're going to see today with the quadratic formula. The last option is the formula. Now, although this is the last one I'm showing, this one always works. Now, some of those other methods are a little quicker if you know when to use them, but this is a fail-safe. No matter what, you can use the quadratic formula. And it will also tell you when things don't have solutions. If we look at an example, it's in that form now. It has a y equals, but we want, for the quadratic formula to work, you need to have it set equal to 0. So you can see that up in the standard form up here. You have your a, your b, your c. They can be rearranged. Something could be on the other side, and you could just think about what it would be. I will actually show doing that in the examples, but it has to equal 0. So once you get it to look like that, you can then look at these three constants, the a, the b, and the c, and you're just going to slap them into the formula. What we're looking for is where would that parabola cross the x-axis? Or if you have it set equal to some number other than 0, where would that parabola cross that line? And it would be a horizontal line. So the formula is, and you're not allowed to have a be 0 because then there would be no x squared, but it's the opposite of b. And then we're actually going to potentially get two possible answers. So it is plus or minus, which means you would do the problem once with addition and a second time with subtraction. But then there's a giant square root sign. We're going to take b squared. That should always be positive. Minus 4 times a times c. And then the whole thing needs to be divided by 2a. Later this week, I will show where this formula comes from. It's not just completely made up. It uses just some solving, things that we already know about from algebra, and then cleaning it up we're probably not used to, so I'll show that. And just to reemphasize kind of the stuff we need to do for the order of using the quadratic formula, it has to equal 0. You're going to find a, b, and c. I like to write them down. Be careful with negatives. And then you're going to slap them into the formula. Everywhere you see an A, put your A number, B, B number, C, C number, and then you're gonna clean it up. And a lot of it can be done in a calculator. So our first example, we have 2x squared minus 11x plus 12 equals 0. Now, one thing I want to point out, you'd always want to first check to see, kind of like from our factoring, does something come out? If A, B, and C were all even, you might want to divide them all by 2. It just makes the numbers easier to work with. You're still going to get the same solutions when you use the quadratic formula. So we have 2x squared minus 11x plus 12, and this one is already set equal to 0. So we can write down our a, which is 2, our b, which is negative 11. You have to be careful. If it's subtraction, it's a negative. And then our c is 12. So we're going to plug our 2, negative 11, and 12 into the formula, and then we'll start to clean it up. A lot of it can be just punched in a calculator. You got to be careful about your order of operations. So I'll kind of break it down to the order that needs to happen. And then also, if you're going to use a calculator, the pieces that you would probably type in, unless you want to go for putting the whole thing in, you're going to need some parentheses. So we have the opposite of b. I like to say opposite because some people think our b is negative 11, and then we see the negative in front of the b, so we think, oh, let's just put down negative 11. But no, it's the opposite of negative 11. So we have 11 plus or minus, then we got our square root, and then we're going to have negative 11 squared. It's going to be positive, so if you're using a calculator, you better put it in parentheses, or you could, for forget about the negative and just know that it should be positive and just type in 11 squared. If you also know that already, you might even just write down, 121 or whatever the number is squared. We have minus 4 times A times C. Again, you don't need parentheses. If there's negatives, it might help with your calculator. And the last part, we're going to divide by 2 times A. So for this first example, I'm kind of showing where everything would go number-wise, and then we'll start to clean it up. But as you do more and more problems, you would probably never do this step. I would, for instance, I would do that denominator as I write it down. Instead of writing 2 times 2, I would write down 4, as well as the negative 11 squared. I would probably write down 121, or possibly even write that entire square root part or type it into the calculator. So if we start cleaning it up, we have that 11 plus or minus. We got 121 inside minus 4 times 2 times 12. All right, so those three are getting multiplied, which is 96. You can do it in your head. Awesome. Calculator, perfectly okay. And then on the bottom, we have a 4. So the next part, in terms of order of operations, we need to do, there's actually 2 grouping symbols that you can't see here. The giant square root symbol is a grouping symbol. So we have to do all of that stuff first before we tackle the numerator, because that's also grouped together, and then finally dividing it by 4. So we have 121 minus 96, which is 25. Square root of 25 is 5, but it's also negative 5. So that is why we have the plus or minus. It accounts for there being 2 possible solutions to that square root. Now, in some like story problem situations, one of those might not make any sense. So you'd have to think about, oh, I'm going to throw that answer out. I can't have a negative here, or whatever the reason is. Okay, we keep going. So we have 11. This is where we're going to break it up into 2. We have 11 plus 5, which is 16 over 4. We also have 11 minus 5, which is 6 over 4. So our 2 answers, if we simplify them a little bit further, 16 divided by 4 is 4. And then the other answer that we can get, 6 divided by 4 is 1.5. So if this were to be graphed, those would be the 2 spots where the parabola is crossing the x-axis. Those are the x-intercepts. All right, next example. A couple things that are a little bit different. It's not set equal to 0, so we need to tackle that 10, get it on the other side, and then we can write down our A, B, and C. Some people jump the gun and write them down first, and it's going to throw it off. Visually, what we would have is we'd actually have a parabola. In this case, it would be upside down because of the negative. And then with that parabola, we would have a horizontal line at 10, y equals 10, going through it. Because remember, the standard form is y equals ax squared plus bx plus c. So this y value is what we're putting in. When it's a 0, we're talking about when y is 0, which is the x-intercepts. But when it's any other number, we're actually talking about, it's like a system. If we had the parabola and a horizontal line, where are they crossing? Story problem-wise, that could be something like maybe someone's jumping off of a diving board and you want to know when do they get 7 feet in the air. So first thing, we're going to move that 10 to the other side by subtracting it so that we have our 0. That's not going to affect the A. It's not going to affect the B. But our C is not 27. It is actually 17. So we have -1 for A, B is 2, and C is 17. A little bit bigger number. But if you think back to that formula, it's only in one spot. It's in that 4AC spot. So the other ones are probably manageable without the calculator. So this is how I would write it down if I was showing a little bit of work, how I would kind of break it up. So I always do that opposite of B. So we got -2 plus or minus my square root. And then I like to actually write down these 2 parts separately. I do the B squared. So B squared, 2 times 2 is 4. And then I also like to do the 4AC part all together. So I don't write 4 times -1 times 17. I would actually write down, now we have a negative in there for our a, so it's actually going to turn into plus, but we have 4 times 1, which is 4, times 17, which is 68. I always do the 2a right away, which is going to give us a negative 2. Okay, start cleaning it up. So we can do that part inside the square root, and we will get to that in a later section that is called the discriminant, but right now we'll just call it the square root stuff. So we have 72. Now, unlike the last one, 72, not a perfect square. So for what we're going to do, decimals, perfectly fine. Other areas you might want an exact answer, so you actually simplify the radical using some of those rules, and then you kind of leave it as this weird looking fraction. So I kind of want to show that for some of you to see it, but in terms of the practice problems, I would just get the decimal answers. So we have, I'll show that first one. So this is the exact answer. 72 can be broken up into 9 times 8, but 8 can be broken up into 4 times 2. So there's actually a bigger perfect square that goes into 72, which is 36. 36 times 2 is 72, but we can do the square root of each one of those separately. So we actually do the square root of 36, which is 6. The square root of 2 is the square root of 2. So it looks like this when the 6 comes out. Okay, now because these three things all have something in common, you can simplify that fraction. So an exact answer, and this might be something you see if you're doing some stuff online. Some people give the answers this way. Some calculators would actually give the answer this way too, unless you change the mode. But I'm going to divide all three of those. You could either divide them by 2 or negative 2. I kind of like the negative 2 idea because for the 6, it's not really going to matter because we have that plus or minus. And then it actually gets rid of the denominator completely. So if I divide them all by negative 2, we get 1 plus or minus 3 radical 2. And that's our answer. So that's the exact answer. You could punch this into your calculator to get those decimal answers, but at the same time, we could show it where you would just get a decimal for the square root of 72 first. So if we do it the calculator way, you can be a little bit more accurate if you actually type in, negative 2 plus the square root of 72. If you don't know how to do that, or maybe your calculator can't do that, you would type in the square root of 72. And then we are going to have to round because since it's not a perfect square, we're getting an irrational number. Tens place, hundreds place is probably fine for what we're doing. So I'm going to go to the hundreds for all the examples that I do, as well as the practice problems. So we have negative 2 plus or minus, we get 8 and 49 hundredths approximately, all divided by negative 2. So now we can break that up into those two answers. So we have negative 2 plus that, divided by negative 2, which gives us negative 3.245. Now, you could round it again. I'm not going to. It terminates, so I think that's just fine. And then for that second answer, we're going to go negative 2 minus our 8 and 49 hundredths. We get 5 245 thousandths. So those are our two answers. And if you want to check, if I type in those other ones before, which was 1 plus 3 radical 2, you get the same two answers. Now they're definitely a little bit more accurate because it's not being rounded till the very end, which is kind of nice. All right, some interesting things if you look at the graphs of that equation. So the original equation with the 10 equals, if I type that in and graph it, what you'll notice, okay, so what you're going to notice with that first one, look where it crosses the x-axis. crosses at negative 3 and 243 thousandths. Again, with that rounding stuff, that is the answer that we had. And then over here, we have the 5 and 243 thousandths. Again, really close to our answers. So really easy way to check it would be just to type it in. Now, some of you might be thinking, well, why don't I just type it in the first place? You don't always have access, to this graphing technology. But for a check, it's pretty nice. Okay, some of the other cases I want to show you. So what if we graphed it without the 10? So what if we graph this equation, y equals the opposite of x squared plus 2x plus 27. So again, we have a parabola. If we look at this one, you might go, well, it's not the same answer. It's crossing at there and there. But if I turn on that horizontal line at y equals 10, well, let's come up here. You look where they cross at our two solutions. So that's truly what's happening prior to us, moving that value over to the other side and getting the 17. This is what's happening if you think about it kind of like a system. If we graph our last one after it's been changed to a 17, now we are again looking at where is it crossing the x-axis. And there's our two solutions. All right, one final one I want to take a peek at. A little bit different than the previous two, not drastically. But again, it's not set equal to 0, so we need to have that happen first. You could move the x squared and the 36 to the right side. They would become negatives. Or you can move the 12x to the left side. It would be a positive. So actually, in every quadratic formula situation, your A, B, and C that you get, you're going to get the same answers if you put in the opposite of A, opposite of B, and opposite of C. It has to be for all three of them, but that will work. So it doesn't matter, left side, right side. So if you're checking a problem and the work looks just a little bit different, that could be the reason why, but the answer shouldn't change. So I'm going to move the 12x to the left side. It's just one thing to move, which gives me an A value of 1, a B value of negative 12, and a C value of 36. So let's go ahead and plug that stuff in. We got the opposite of B, which would be 12, plus or minus the square root. B squared is going to be 144, minus 4 times A times C. So 4 times 1 is 4. 4 times 36 is 144. All over 2 times 1, which is 2. Now what happens here that's really interesting is that discriminant thing. That part inside that square root comes out to be 0. The square root of 0 is 0. When you add 0, nothing happens. When you subtract 0, nothing happens. So we actually don't get two answers. We only get one answer, which is the 12 divided by 2, which is 6. If we were factoring this is one of those cases where both of the binomials had the same answer. So you only wrote it down once. Visually, what's happening? Let's graph it again. So we got a couple interesting things when we just type in the original problem, x squared plus 36 equals 12x. You can see I can zoom out as far as I go, and it's only crossing one time. It's just one vertical line right here at 6. If we graph the other one, which has it not set equal to 0, but set equal to y, and we look where it's crossing the x-axis, that vertex is right on it, and that's why there's only one x-intercept. Therefore, there's only one answer.